Welcome to the lecture for section 1.1 on angles in standard position. So when we talk about angles in standard position, we want to put an angle on the XY coordinate system. So looking at this diagram here, here's your x-axis and here's your y-axis. So we say the vertex is at the origin, and what we mean by a vertex is that this point right here is the vertex. The sides of your angle are rays. So the initial side, we say, lies on the positive x-axis. So here's my initial side, which lies on the positive x-axis. Then the terminal side will indicate the amount of rotation of the angle. So the terminal side is also a ray emanating from the origin, but it can be anywhere here in the whole 360-degree range. So we sweep using an arc as an indicator of which direction and how much sweep we have, starting at the initial side through to the terminal side right here. And so we can see that this angle is this size here, which is 135 degrees. All right, we also have direction. So positive rotation is counterclockwise. So that would mean this is a positive rotation. Negative rotation is clockwise. So that would be negative rotation here. So not only does this indicate size here, this arc, this arrowhead on the tip of it indicates direction. So since it's pointing in the counterclockwise direction, we say this is a positive angle. Since this arrowhead is pointing in a negative direction, we say this is a negative angle. So we swept through 45 degrees in the negative direction from the initial side to the terminal side. Okay, let's review this one here. We've swept through 135 degrees in the positive direction from the initial side to the terminal side. So we're going to sketch these 4 angles in degrees in standard position. So I'm going to make 4 little diagrams. So the first one, negative 240 degrees. I'm going to go in the negative direction. So this is negative. And I'm going to count 240 degrees. So each quadrant would be 90 degrees. So I would go 90, 180, 270, but that's too much. So I'm going to back off 30 degrees. So I'll be here. And this will be my terminal side. So initial side always lies on the positive x-axis, and the terminal side sweeps through the rotation. So if I draw my arc, I would be going 90, 180, 240 in the negative direction. The next one is 100 degrees in the positive direction. So I'm going to go 10 degrees past the vertical, and my arc will go 90 plus 10, so that's 100 degrees. So this is my initial side and my terminal side. The next one says negative 50, so this was positive, this is negative. So 50, so 45 degrees would be right in the middle here, so 5 degrees past that, so right here. So this would be my initial side, my terminal side, and I've got 50 degrees in the negative direction. All right, one more. So once again, we're in the positive direction. 20 degrees. So that would be about here in the first quadrant. This is my initial side. So my arrowhead indicating direction. So this would be 20 degrees. So now let's talk about radians. So a radian is a standard unit indicating the measure of an angle. So we know about degrees already. Degrees are the other standard units of angle measure. We're more accustomed to degrees, but let's see what we mean by a radian. All right, so now if I look at my diagram over here, I've got a radius from here to here, and I've got another radius from here to here, and then I can think about a flexible radius. So a flexible piece the same length as one of these radii here, and I drape it over the outside of the circle here, and where these 2 points connect the ends of this flexible radius, I've created what I call a radian. So this amount of sweep right here is how big a radian is. So we can see a radian is a much larger unit than a degree, because we know there are 360 degrees in one circle. So if there are 360 little pieces of pie, if you will, skinny pieces of pie that fit in a circle, they're very, very small. All right, it's hard to even draw one that small, compared to a radian, which is a much larger piece of the circle, a much larger piece of pie. Now, what's really interesting is how this ties into something we already know about circles that we've known a while, and that's the circumference of a circle. So if I try to figure out how many of these R pieces would fit on the outside of any circle, it turns out that there are 2 pi of these R's that fit on any circle. So that we know is the circumference of a circle, and that's where that comes from. So 2 pi times R, the radius of the circle, tells you the distance around any circle. All right, so that's where that comes from. So when I say 2 pi, I mean 6.28 approximately. So that would be 1, 2, 3, 4, 5, 6, and then like a third of a radius would fit on the outside of any circle. All right, so the radius of the circle is independent of the size of this angle, of course, because it's similar to how you think about similar triangles. They're just enlargements of one another. So circles are enlargements of one another, and all circles are similar in that, that they're perfectly symmetric around the origin. All right, so a radian is a radian, regardless of the size of the circle. It's independent of the radius of the circle. All right, so 360 degrees is equivalent to 2 pi radians. All right, and we use that to come up with a conversion factor to convert between degrees and radians, both of our units of measure, similar to how we would convert between inches and centimeters or kilometers and miles, that idea. So we're going to label these 2 circles according to how we're going to label our system of angles in standard position. So we start out here at 0, so this is 0 degrees, and then we go 90 degrees, so this is 90, so each quadrant will be an additional 90 degrees, so this will be 180, 270, and then a full rotation would be back to 360 degrees. So if we do it in radians, this is our starting position, 0 radians, and let's look at one full revolution, which would be 2 pi radians. And we'll go from there. So we already discussed how one full circle is 2 pi radians. 2 pi radians lie on the 2 pi radii lie on the outside of any circle. So then half of that would be here, so that would be pi radians. And then half of pi would be pi over 2 radians. So then what's going on here is I've got each quadrant is pi over 2. So pi over 2, then this would be 2 pi over 2, which reduces to pi. So that would make this 3 pi over 2. And then full circle would be 2 pi. So pi over 2 corresponds to 90 degrees, pi to 180, 270 to 3 pi over 2, and 360 to 2 pi. So let's learn how to convert between degrees and radians. So we just got through demonstrating how there are 360 degrees and 2 pi radians. So we can set an equality here, 360 degrees equals 2 pi radians. So if we want to form a conversion factor is a ratio that's equivalent to 1, so that when we multiply a quantity by a conversion factor, we're not changing the magnitude of the quantity, we're just changing the units. So we call that a conversion factor. So you've dealt with those in science quite a bit already. So we need to do this sometimes when we're converting weight units or mass units or length units, sometimes even degrees of temperature. Right? So now we're going to talk about converting units of angle measure between radians and degrees. All right, so we've got our conversion factor. So in one direction, if we want to convert degrees to radians, we would want the degrees to cancel. So you would have degrees here and degrees here, one on the top, one on the bottom. The radians, which you end up needing on the other side of the equals, would be on the top. All right, so degrees would cancel. So if you start out with the radians and you want to end up with degrees, you flip the conversion factor. So you'd have radians and radians, which would cancel, and you'd end up with degrees on the right. So in this example, we're going to convert from degrees to radians and leave pi in our answer. So the first one, let's call it A, 210 degrees. So we want the degrees to cancel. So the 180 degrees is going to be in the bottom, and the pi radians will be in the top. Turns out that we don't often write the units radians. You very well could, but most of the time we just leave it off. It's just understood to be there. All right, so now I can see that my degrees will cancel. So I'll be left with 210 over 180, and pi would be in the numerator. So I can reduce this fraction here. So 3 goes into 21 7 times. 3 goes into 18 6 times. So I've got 7 pi over 6 radians. So 30 degrees, we're going to do it the same way. Multiply by our conversion factor. We'll leave off the radians this time. Degrees will cancel. So you're left with 30 pi in the numerator, 180 in the denominator. Zeros are canceled. 3 goes into 3 one time. 3 goes into 18 6 times. So we're left with pi over 6 radians. let's just go ahead and indicate those are our results. Okay, C, I've got a negative angle in degrees. Convert it to radians, multiply by the conversion factor. Degrees will cancel, so you'll have a negative angle as a result as well. Nothing happens to the negative sign. Reduce. So I have negative, let's see, 6 goes into 30 5 times. 6 goes into 18 3 times. So this is my result in radians. One more. 58 degrees. Convert to radians, conversion factor. Degrees cancel. So I've got 58 pi, 180. So dividing by 2, 29 pi, 90. Okay, so this is my radians. Okay, so we generally leave these with the pi in them in a reduced fraction format. Occasionally, you'll see radians as decimal numbers like 2.5 radians or something like that. But most often, we're going to see them in our work as reduced fractions with a pi in the numerator. Okay, here we're going to convert from radians to degrees. So you will have your calculator that you can use. So I'm going to multiply by the conversion factor. This time the radians are going to cancel. So top, bottom, radians. So pi will cancel out. So you're left with 180 over 4 degrees. All right, so the degrees are left. So I can reduce that to 90 over 2, which is 45 degrees. All right, next, I've got negative 5 pi over 6. So once again, the conversion factor, 180 over pi. Pi's will cancel, and in the calculator, you can type in negative 5 times 180 divided by 6. And that would be negative 150 degrees. All right, next one, 1.5 radians. All right, so that already is radians. If I want that to turn into degrees, conversion factor with the degrees on top. All right, so typing that into the calculator, 1.5 times 180 divided by the pi button. Let's round it, 85.94 degrees. All right, one more of these, 3 pi over 16, 180 over pi, so the pi will cancel, pi's will cancel. So I've got 3 times 180 divided by 16. Let's just write that as a decimal number. 33.75 degrees. So next, let's talk about DMS, or degrees, minutes, seconds. So the symbols would be still the degree symbol, 1 tick mark for minutes and 2 tick marks for seconds. So degrees can be broken down into minutes and seconds, much like hours can be. So it's a base 60 system, the same as hours, minutes, seconds. So this is used for land surveying devices and GPS. We can convert between DMS and decimal form for angle measurements, and I'm going to show you how that works. Okay, so let's convert between degrees and DMS in both directions. So A says convert this decimal number here to degrees, minutes, seconds. So I look for my whole part. So that would be 233 whole degrees, and I start there. So I have 233 degrees. And now the decimal part, 0.378, those are my partial degrees. So 0.378 is going to be your minutes and seconds. So minutes and seconds are part of a whole degree. They're smaller than a degree. So first, to get the minutes, I multiply by 60 minutes, and that gives me 22.68 minutes. So I have 22 whole minutes, and now I need to figure out my seconds. So I have 0.68, that's my partial minutes, so that would form my seconds. So I'm going to multiply that by 60 seconds, and I'll get 40.8 seconds. Now I put it all together. I've got my D part, that's my degrees, my M, that's my minutes, my whole minutes, and then 40.8, that's your seconds. So we just leave that 0.8 on there because we don't get any smaller than seconds. All right, so that's your answer. That's your conversion. Now to go the other way, I've got DMS, and I want to go to degrees, so this is actually an easier calculation. So I've got 279 whole degrees plus, now for my minutes, I've got 40 out of 60, so that's a partial degree. And then I've got 23 out of 3600 seconds per whole degree. So that's 60 squared. So it's the same thing for hours. You would have 60 minutes in an hour, but 60 times 60 seconds in an hour. All right, and you add this all up. If you were talking about hours, it would be a similar calculation. But if I want to get the degrees, I just go ahead and type this in as a sum. So plus in between this, and you end up with 279 to the left of the decimal, and then to the right of the decimal, 0.673. All right, so that gives me in decimal form my number of degrees. So coterminal angles are two angles that have the same initial and terminal side. So we take a look at this picture over here. We can see that this being your initial side, of course, this is your terminal side. The red one starts on the initial side, ends on the terminal side. But the blue one does as well. It starts on the initial side, ends on the terminal side. You can see that they have differing degree measures, though. This is a smaller angle than this one here. And they have different directions. This is a positive angle. This is a negative angle. If we look at this example, initial side here, terminal side here. This is a positive angle that goes from here to here. And this is also a positive angle, except it goes around an additional rotation. These are coterminal angles because they have the same initial side and the same terminal side. All right, but differing amounts of rotation. All right, so let's talk about those a little bit more. So let's look at an example. So we're going to find some coterminal angles here in degrees. So this one says find an angle in this interval between 0 and 360. So the way you interpret this is 0 is included in the interval, 360 is not. All right. And we want this angle to be coterminal with negative 1138 degrees. All right, so the way that we do this is we start at the given angle and we keep adding full revolutions until we get into the interval 0 to 360. So you do this on your calculator. Type in add 360. Nope, I'm not there yet. Still negative. Add 360. Still negative. Add 360. Still negative. So I'm looking at my number that I'm building. Let's try it one more time. Add 360. Finally, I get a positive degree measure. I got 302. So I had to add 4 revolutions, 1, 2, 3, 4, to get my angle up into this positive range here. So 302 is definitely between 0 and 360. So that would be my coterminal angle that fits this requirement. It has to be in this range. For B, we're going to find an angle in the interval negative 720 to negative 360, coterminal with 955 degrees. So we're going to start out with 955, but this time I'm going to keep subtracting full revolutions, and that's not enough to get down in the negatives. I have to be negative. Let's do it again. I'm looking at my calculator as I'm doing this. That's still not enough. Let's do it again. Nope, still not enough. Let's do it another time. All right, and now finally I get down into the negatives. Actually, below negative 360. You can't just be negative on this one. You have to be in this negative range, negative 360 to negative 720. So I got negative 485, and that is definitely between negative 360 and negative 720. So this is a coterminal angle that fits that requirement. So this is what I'm looking for. Okay, so now let's work with angles in radians. So this time we're going to add or subtract 2 pi because 2 pi is 1 full revolution. So A says find an angle in the interval 0 to 2 pi, which is coterminal with 31 pi over 8. So first of all, 2 pi in terms of eighths would be helpful to know so we can make a comparison. So 2 pi in terms of eighths is 16 pi over 8. So we're looking for an angle in the interval 0 to 16 pi over 8. That's coterminal with 31 pi over 8. All right, so I need to get that 31 pi over 8 smaller to get it in that interval. So I'm going to subtract 2 pi. 2 pi is 16 pi over 8. All right, so that gives me 15 pi over 8. Well, I can see that 15 is less than 16, so I am now in this interval. So this angle fits the requirement that the coterminal angle has to be within 0 to 2 pi. All right, let's try another one. This time, I'm restricted to finding a coterminal angle between negative 4 pi and negative 2 pi. All right, so let's see what that would be in terms of eighths. So negative 4 pi in terms of eighths, that would be negative 32 pi over 8. Negative 2 pi in terms of eighths would be negative 16 pi over 8. So our interval would be between negative 32 pi over 8 and negative 16 pi over 8. All right, so I've got negative 3 pi over 8 that I'm working with. All right, so it needs to go down lower than that to get within the range I'm interested in. So I'm going to have to subtract 2 pi. So that would be 16 pi over 8. So that's negative 19 pi over 8. All right, that's definitely between negative 16 and negative 32. So this angle here will work. Okay, now we'll talk about arc length. It's another concept having to do with angles. So I have a circle, and I have a pie-shaped sector, so to speak. So the center is here, of course, a radius here, a radius here. So this bounds this arc S in my diagram here between these two radii. I'm interested in finding out the length of this arc. So the formula for finding out the length of this arc is the length of the arc S is equal to the radius times the angle here. All right, so this is the angle subtended by the central angle theta. All right, so in this formula, theta must be in radians. Okay, so if it's in radians, we go ahead and plug that angle right into the formula. If it's in degrees, we would first convert it to radians and then plug it into the formula. So here's an example. We're going to find the arc length of a circle with a given radius. So here's my radius, which is subtended by a central angle either given in degrees or radians. So my first example is given in radians. So I don't have to convert my angle to radians. So my formula, S equals R theta. So S is equal to 7 feet times my angle in radians, which is 31 pi over 8. So I'm going to get a decimal number out here. So 7 times 31 times pi divided by 8. So if I plug those numbers into my calculator, that operation, I'm going to get 85,216, and the units will be feet. So arc length is a linear unit, like feet, miles, inches, that sort of thing. So my arc is that long. So let's try one here in degrees. So my central angle is given in degrees this time. So I need to convert the degrees to radians. So with my conversion factor, I want the degrees to cancel. So my conversion factor will be this way. So my degrees will cancel. And I end up with, let's get a number here. So I'm just going to use a reduced fraction, 25 pi over 36 radians. All right, so now take that, plug it into your S is equal to R theta formula. Radius is 8 kilometers. Angle is 25 pi over 36 radians. So I'm going to type all that into my calculator, and I'm going to get 17,453.453 kilometers. This is the length of my arc. Now in this example it says find the central angle in degrees or radians of a circle with a given radius which has the given arc length. So we've got the same formula. However, what we're interested in is the angle. So theta is equal to S divided by R. All right, so I'm going to solve for theta given S and R. All right, so arc length is S, so 15.3 centimeters in the numerator. The radius, 10.5 centimeters. So the centimeters are going to cancel. And you'll be left with a number here. Let's see what I get. 1.457. And this is going to be in radians. Okay, so remember our formula has theta in radians. All right, so now I take my radians and I'm going to convert that to degrees. So I want the degrees on top and I want the radians to cancel. So I type in 1.457 times 180, divide by pi, and I'll get a degree measure out. So that turns out to be 83.49 degrees. Okay, so this will be my angle theta in degrees. The next one, B, You're given a radius and an arc length once again, but this time we want the angle in radians. So we've got the formula. We're interested in the angle. The arc length is 0.75 miles. The radius is 2.1 miles. So the angle in radians is 0.357 radians. Okay, so this is a radian number, even though it doesn't have pi in it. This is an amount of rotation given in radians. So 0.357 radians is what I'm looking for here. Okay, so one more thing having to do with central angle. We're going to talk about the area of a sector of a circle. So a sector of a circle is a region of a circle enclosed by an arc on the circle itself and two radii. So this pie-shaped piece right here is called a sector. And we're going to find that area. So the units will be squared units. All right, so the way that we do that is we proportion the area of the entire circle by the amount in the sector, theta, over the entire amount, 360 degrees, and if we're working in degrees, or 2 pi if we're working in radians. So here's my proportion in degrees multiplied by pi r squared, which is the area of the entire circle. And then if I'm working in radians, here's my proportion, the angle over a full revolution multiplied by the area of the entire circle. So we're going to find sector area, and we're going to include our units of area and round to 3 decimal places. So we've got a radius. Let's just make a little sketch here. A radius of 30 feet. We have a central angle of 78 degrees. So we're interested in finding the area of this sector here. All right, so we know that the area of a full circle is pi r squared, where r is 30. All right, we want to proportion that by what we have, what portion of the circle we have. So we have 78 degrees of the circle out of a total number of degrees of 360. So we type that into the calculator, pi times 30 squared times 78 divided by 360. So we're going to get a decimal number here. So this is going to be an area equal to 612.611. So my radius is in feet, so my area is going to be in feet squared. All right, so this is what we're looking for. So however much rounding you do will be dependent on what you're asked to do. Now let's try one where the angle measurement is in radians. So we've got our circle, we've got a radius, we've got a central angle equal to 2 pi over 5. So I'll just estimate the size here. So that's about a half a pi. So a little less than a half a pi, where pi is a 180 degree slice. So let's just say it's about this much. All right, so we've got, if we were talking about the full circle, it would be pi times r squared. But we're only talking about a portion of that 360 degree circle. So we're talking about 2 pi over 5 radians out of a total of 2 pi radians. All right, so you're going to cancel out the pi's here. So the way that you can enter it is in 2 steps. First, you can either type that all in just looking like that if you wanted to, or you can, just so that you don't mess up your calculation accidentally, you can type in this part, and that'll give you some number in your calculator. Then go down to the next line and divide the whole thing by 2. That's one way of doing it. Or you can just type in the whole thing like that. So then what you're going to end up with is an area of 141,372 kilometers squared. So those are squared units of area. So I recommend that you go ahead and figure out how you're going to type this expression here into your calculator. Make sure you're able to come up with this number here. All right, so that when you get one problem like this, you know the steps you're going to take to get it into the calculator. All right, so that's my area. Okay, so that's all the examples I have having to do with section 1.1, which is our introduction to angles, now that we're into the trig unit. So this should be enough to get you started on your homework assignment. So you have until Sunday at midnight to get your 1.1 assignment submitted. So let me know if you have any questions as you're working on these problems.